So what we're going to start to look at in Chapter 2 is modeling distributions of data, and what we're going to look at first here is describing location in a distribution. So that's essentially going to amount to two things for today. One is what's known as a percentile, the other of which is what's known as a z-score. And we'll first take a look at some different things involving percentiles. So one of the different measures of location is a percentile. So what you're basically looking to find when you are computing the percentile rank of a given data value is you want to know what percentage of the entire data set falls below a given data value. So to compute a percentile, what you will basically do is you will take the number of data values that fall below a given data value and you would divide it by the number of total data values. So here's an example of a percentile problem, and it has the scores of all 25 students in an AP Statistics class, and this is the grades that they received on their first test. And what I want to know here is, here's Jenny. She scored an 86 on her first test. And what we want to know here is, what is her percentile rank? Meaning, what percentage of students did she do better than on this particular test? So what I want to basically do here is I want to take, if you notice, we took the 25 data values and made a stem and leaf diagram out of that. And that's just so the numbers are in order and it's easy to see how many different data values there were that fell below the 86 that she happened to score. So in order to find what her percentile rank is, what I want to do is I want to count how many data values there are that are below 86. So if I go through my diagram here, it's basically these numbers here, and if I count all those up, there are 21 scores that her score was better than. So to find what her percentile rank is, I would take the 21 scores that she scored better than out of the 25 total scores, and that would get me 0.84, which is 84%. So what that means in terms of position and what that means in terms of percentile rank is that her score was 84%, or 84% of the students, she scored better than 84% of the students that took this particular test, which puts her percentile rank at the 84th percentile. So the higher your percentile rank in this particular example here, the better that she does on this particular test in relation to the other students that were in the class. So just kind of moving forward with some other things here. And this table here, if you notice the title, we're going to talk here about cumulative relative frequency. And the graph for that is what's known as an ogive. So the data that I have here is, this is the age of the first 44 presidents when they were inaugurated. How old was each of the presidents, the first 44 presidents, how old were they when they were first inaugurated into office? So you have broken up by age groups here. We got the 40 to 44 years of age. There were two presidents who were anywhere from 40 years old to 44 years old when they were inaugurated. You have 7 presidents that were anywhere from 45 to 49 years old. There were 13 presidents that were anywhere from 50 to 54 years old. We have 12 presidents that were anywhere from 55 to 59 years old. We have 7 presidents that were anywhere from 60 to 64 years old. And finally, we had 3 presidents that were anywhere from 65 through 69 years old. So this first column here, this relative frequency, what we basically want to know is what's the percentages for each one of those age groups. So you have this right here first. So it's out of 44 presidents, okay, 2 of them were anywhere from 40 to 44 years old. So you have that percentage being 4.5. 4.5% of the first 44 presidents were inaugurated anywhere from ages, or first inaugurated anywhere from ages 40 to 44. Then we move on to each of the different age groups here, and this is the percentage of presidents and their age group of when they were how old they were when they were first inaugurated. So that's just the relative frequency. If you take a look at this second column, the cumulative frequency, and what we're measuring there is the cumulative frequency. So we're basically taking this first column here, and we're basically just keeping a running total of how many presidents were that age, or in this case, younger. So for the first age group here, there were 2 presidents that were anywhere from 40 to 44 years old when they were first inaugurated. If you take a look at the second row here, you have a value of 9. And what this 9 represents is there were 9 presidents who were anywhere from ages 40 to 49 years old. So what we basically did to get this 9 was we took this 2 and this 7 and we just added those together. And that's where the whole cumulative part of this comes in when we're talking about cumulative frequency. So if I go to the next row, this 22, where does this 22 come from? Well, what we're basically saying here is that there were 22 presidents who were anywhere from 40 to 54 years old when they were first inaugurated. So what I did to get the 22 was I added the 2 here, the 7, and the 13 to get that. So I'm just keeping a running total of how many presidents there were for each of the different groups here. So the 34 for this, now this comes in, we're talking about how many presidents were inaugurated anywhere from age 40 to age 59. So I get this 34 by adding the 2, the 7, the 13, and the 12 here. And that's where that comes from. And then if you take a look at this one here, the 41, okay, that is, there were 41 presidents who were ages anywhere from 40 to 64 when they were first inaugurated. And that comes from basically adding the 2, the 7, the 13, the 12, and the 7 here. And then finally you have 44 presidents that were inaugurated that were anywhere from 40 to 69 years old when they were first inaugurated. So that's where the cumulative frequencies come in. And then if we're talking about the cumulative relative frequency, and that's where we take our frequencies and convert them to percentages. So if you take a look at this column here, it's still out of 44, but notice what we have here. So for this first group, we're basically saying that 4.5% of the presidents, the first 44 presidents, were inaugurated anywhere from were ages 40 to 44 when they were first inaugurated. Then you have this group here, this 9 out of 44. And that was, there were 9 presidents who were anywhere from 40 to 49 years old when they were first inaugurated, et cetera, et cetera, et cetera there. So in terms of the graph for this, okay, this graph right here is representative of this data right here. This is the cumulative relative frequency, and the name of this graph is what's known as an ogive. Okay, and an ogive is simply just a graph of the age groups and their cumulative relative frequencies. So it's the first column here and the last column here is what I'm graphing. And these kind of graphs are very good for determining percentile ranks. These graphs are very good for looking at some different things involving the 5-number summary, the first quartile, third quartile, different things like that, because this is all based on percentages. So some of the different things that we've measured with percentages apply to this type of graph here. So just kind of moving forward here, and here's the graph that we just that I just showed you. And the question, there's a question that goes with this, and it says, use the graph below to answer the following questions. So the question here says, was Barack Obama, who was inaugurated at age 47, was he considered unusually young in comparison to the other 43 presidents? So if you take a look at, we have the ages on the bottom here. So here's where 47 basically, or approximately where 47 would be on the graph. And if I take the percentage of presidents that were inaugurated below that point, I end up with this over here. I end up with 11%. So what that means in terms of an interpretation is I would say here that 11% of all U.S. presidents were younger than Barack Obama when they were inaugurated. Or to put it another way, Barack Obama was inaugurated at a younger age than about 89% of U.S. presidents. So to answer this question of this whole business of unusually young, one of the things, statistically speaking, that we classify as unusual is anything that happens 5% or less of the time. So even though 11% is a pretty low percentage, and it is something that doesn't happen quite often, we really don't consider that to be unusual because it doesn't really meet this 5% threshold. So to kind of answer this question here, would we say he's unusually young? We would, statistically speaking, we would say no, he's not unusually young. It's not a very common occurrence, but it's not uncommon enough for us to say that it's unusual. So another example that kind of goes with this, and the question says to estimate and interpret, big thing there, interpret, the 65th percentile of the distribution. So what I want to basically do first is I want to figure out on this graph right here, where is or what point would be considered approximately the 65th percentile. So if I go up to where 65% would be, or approximately 65% on this vertical axis here, this is approximately what you get there. And then all I really want to know is approximately, if I drew a line from that point going straight down to the horizontal axis, approximately what age would that be? So based on the data that we have, we're approximating that the 65th percentile would be roughly at around 58 years old. So that's the estimate, but what about the interpretation? So this is how you typically would want to interpret something like that. We would say that about 65% of all U.S. presidents were younger than 58 when they took office. So that's just a real quick and easy way that you can take a percentile and create an interpretation of it. Now just remember, when you interpret, notice that this is within the context of what we're talking about. Okay, so just make sure that when you interpret something, that you interpret it with the backdrop of the information that we're discussing here. So that's just some different things with cumulative relative frequency. That's just some different things with what's called an ogive. So what I would like for you to do at this point is take a moment and pause your recording here and attempt to answer these problems here. There's a couple checkpoint questions. Attempt to try to answer these questions on your own. And then once you're finished, come back and push play and match your answers up with what we have here. So the first question here, it says, Mark receives a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of 39, which placed him at the 68th percentile. What does this mean? So if you take a look just answers-wise at this, the answer to this was C. Mark did better than about 68% of the students who took the test. And notice the key thing here is he did better than about 68%. All right, because that ranks him at the 68th percentile, so that means he scored better than 68% of the students who took this test. For question 2, it says, Mrs. Munson is concerned about how her daughter's height and weight compare with those of other girls of the same age. She uses an online calculator to determine that her daughter is at the 87th percentile for weight and the 67th percentile for height. Explain to Mrs. Munson what this means. So what this question is asking you to do is to interpret both of these percentiles, one for weight, one for height. So you have this first, okay? Her daughter weighs more than 87% of the girls her age, and that basically speaks to the first percentile. And then the second percentile, the 67th percentile, that means that she is taller than 67% of girls her age. So just once again, notice that we're interpreting this in the backdrop of the question. We're interpreting this in context. Okay. Question number 3 was a question about an ogive. Kind of slide this over here, and it says the graph displays the cumulative relative frequency of the lengths of phone calls made from the mathematics department office at Gabalot High last month. About what percent of calls lasted less than 30 minutes? So if you take your graph here and we go to the 30-minute mark on the x-axis, and I just kind of draw a line going straight up to here, okay? If we can get a better line with that, but here's the 30-minute mark, and then all I want to do from here is just kind of draw a line straight across to know what percentage that would be. So if my line was a little bit better here, you would see that it's about 65% of the calls that lasted less than 30 minutes, which on the flip side of that would mean about 35% lasted longer than that. And then question 4 asks you to estimate the first quartile, the third quartile, and the interquartile range of the distribution. So just remember a couple things with this. Remember that Q1 represents the 25th percentile, okay, and Q3 represents the 75th percentile. So if I go to where 25% would be here and 75% would be, I don't know, maybe somewhere like that, okay, I just want to know what these values are for Q1 and Q3, and to find the interquartile range, I'm just going to subtract the answers to that there. So once again, we're talking approximations here. The first quartile came out to be approximately 14 minutes. The third quartile came out to be approximately 32 minutes, which makes the interquartile range for this 32 minus 14 would be 18 minutes. So that's the interquartile range for that there. So that's one example of some different things involving measures of location. The other thing is z-scores. It's a different measure of location. So a z-score tells you how many standard deviations from the mean a particular data value falls. And notice here, and it also says, and in what direction. So a couple quick things about z-scores. One is a positive z-score represents a data value that is more than the mean. A negative z-score represents a data value that is less than the mean. So in terms of how you find a z-score, and here's the thing, another name for a z-score is what's known as a standardized score or standardized value. So sometimes you hear z-scores referred to as standardized scores, and if you do, that's basically what they mean there. But here's the formula for a z-score. You have the data value minus what the mean is divided by the standard deviation of the data set. Okay, and that's where the whole standardized value comes from, what the z-score comes from. So it basically measures how many standard deviations from the mean a given data value is. So if we go back to the question that we had before when we were looking at percentiles, and it says Jenny earned a score of 86 on her test. The class mean is 80. So she scored slightly above the mean, and the standard deviation was 6.07. What is her standardized score? So right off the bat, hopefully you notice here, her score of an 86 is better than the class mean of an 80. So what that means is when you go to compute her z-score, her standardized score, this value should come out to be a positive number because her score was better than the mean. So in terms of what you would plug in here, so we're going to do for this here, the data value minus the mean divided by the standard deviation, and this is what I get, 0.99, which is approximately 1. So what that means is her score was approximately 1 full standard deviation above the mean. And we'll get into looking at in a few weeks in terms of percentages what the significance of knowing that type of information represents. What we're going to use this a lot for now is just some different things in relation to comparisons, comparing one data set to another. So here's an example, and it says Jenny earned a score of 86 on her statistics test. The class mean was an 80, so that was the data that we just kind of came up with. Standard deviation was 6.07, so that was the score for her statistics test. In another class, this is her chemistry class, she earned an 82 on her chemistry test, and the chemistry scores had a fairly symmetric distribution with a mean of 76 and a standard deviation of 4. On which test did she perform better in comparison to the rest of her class? So what I want to do here is I want to compute a z-score for both her statistics test and for her chemistry test and see which of those two scores did she score better in comparison to the rest of the students in her class. So if you take the statistics data first, which we already did on the previous question, we got 86 minus 80 divided by 6.07. That gets a z-score of roughly 0.99. Then if you take the chemistry test, she has an 82 minus 76 divided by 4, which is 1.5. So she scored approximately 1.5 standard deviations above the mean on the chemistry test. So which of these two tests did she do better on? Well, obviously, if you're talking just from a score on the test, she did better on the statistics test because she got an 86 on the statistics test, but only an 82 on the chemistry test. But if we're talking about comparing her results to the rest of the class, she actually did better on the chemistry test because she scored higher above the mean than she did with the chemistry test than she did on the statistics test. She's 1.5 standard deviations above the mean on the chemistry test, but only approximately 1 standard deviation above the mean on the statistics test. So once again, here's some checkpoint questions. So what you want to do at this point here is just pause the video, take a few minutes to answer these checkpoint questions involving some different things with z-scores. So picking up with the first checkpoint question here just to see if what you did was right. It says Mrs. Navarre's statistics class has just completed the first 3 steps of the Where Do I Stand activity that we did in class. The figure below shows a dot plot of the class height distribution along with summary statistics from the computer output. So here's the dot plot that they came up with. And this represents all the different heights of the students in our class. And then you have this at the bottom. And let's just talk just briefly about what's in here. So you have the value of n, which is 25 students. Here's the mean, x bar 67. Here's the standard deviation, 4.29. And then they give you this at the end. Here's the 5-number summary, which would speak a little bit to percentiles if we needed to do some different things with that. So the question here says, Lynette, a student in the class, is 65 inches tall. Find and interpret her z-score. So in terms of what we're going to do mathematically here, right, I want to take her height minus the mean divided by the standard deviation. When I do that, I get negative 0.466. So hopefully you notice here that since her height is less than the mean height of the students in her class, you're going to get a negative value for the z-score. So in terms of interpretation for this, okay, what we would say is Lynette's height is about 0.47 standard deviations below the mean height of the class. And once again, I know that it's below the mean height, one, just from looking at the data values, but also from looking at the sign of the standard of the z-score. I get a negative z-score, which means her value is going to fall below the mean. And then question number 2 here, another student in the class, Brent, is 74 inches tall. How tall is Brent compared to the rest of the class? So when I take this, once again, we're talking about z-scores. I take Brett's height, 74 inches, minus the mean, divided by the standard deviation, and I get 1.63. So what that means is, because it's a positive value, Brent's height is above the average. So interpretation-wise, we would say that Brent's height is about 1.63 standard deviations above the mean height of the rest of the class. So just make sure that you answer these when you interpret them in context. Above the mean height of the rest of the class. Below the mean height of the class. All right, you always want to make sure you're giving this in terms of the context of the problem. Okay, and then question number 3. Brent is a member of the school's basketball team. The mean height of the players on the team is 76 inches. So that's the mean height for all the players on the team. Brent's height translates to a z-score of negative 0.85. What is the standard deviation of the team member's height? So a couple things here. First is, notice that the z-score for Brent in comparison to the players on the basketball team, notice his z-score is negative. So what that means is Brent's height is going to be less than what the average is. So if we talk about just setting up an equation here, right, I'm going to first fill in the negative 0.85 for z. I'm going to fill in Brent's height, which I know already is 74 inches. I know the mean of the basketball team's height is 76 inches. And then I just want to take this and I want to solve it for the standard deviation. So, one of the things you could do here is you could just put this over 1 and cross multiply. Okay, I mean, there's obviously a couple different ways you could solve this, but in any event, the mean for this is 2.35, or the standard deviation for this, excuse me, is 2.35 inches. That's the standard deviation for the height of the members of the basketball team. So that basically talks about some different things with measures of location. One of the things that we're going to look at next is going to be how you transform data, meaning if you take a group of data values and you add the same value to it, what does that do to your different measures of location and things like that? If you take all your data values and you divide it by a certain data value, what does that do to all the measures of location and things of that nature?